This is Math 251, section 12.2, and we're looking in this section at graphing our multivariable functions using level curves. Level curves are actually something that you've probably seen before if you've ever looked at a topographical map. Those are actually what's known as level curves. Mathematically, the intersection of a surface, z equals f of x and y, represented by this sort of a hill-shaped surface here, with the plane z equals c, it's going to be a horizontal plane slicing through our surface, is called a contour curve of the surface. So they didn't actually draw the plane in this one, they did do so more in the bottom of the page if you look down. But if you imagine that horizontal plane, z equals a constant, slicing through this hill, then this elliptical shape right here is called the contour curve. If I take that contour curve and I project it down into the xy plane, which is what this dotted line is, that's what's known as the level curve. So contour curves exist at whatever height they were in the original surface. Level curves are the contour curves that have all been flattened down into the xy plane. In this next picture, you can see a little bit better how they've shown us several, or at least a couple of z equals a constant. Here was z equals z1, and then this darker one is z equals z0. They've sliced through to create those two contour curves. And then you can actually see where they've graphed them over here. The z equals z0, this one, corresponds to this level curve in the xy plane. And then the z equals z1, the one that was a little higher up, that corresponds to this level curve. You'll note they've also graphed a couple of other level curves that they didn't show in the three-dimensional object. So these are the contour curves. And these, as it says, are the level curves. One quick note, how does the spacing of the level curves relate to the shape of the surface? The closer together the level curves are, the steeper the original surface. You can see in here you've got a couple that are getting closer together. It's because this is slightly steeper as we go up. So, for evenly spaced z equals c planes, so I'm assuming now that I'm slicing through at evenly spaced locations, the more closely spaced the level curves are, the steeper the surface. Just tells you it's going up faster. All right, we're going to do one example that we'll completely do. We'll actually start with a function. We will calculate some level curves and graph them and see if we can predict what the original surface looks like. And although it works, I think you'll see that it's a rather time and labor intensive way to predict what the graph of a surface looks like. Of course, we've got good technology to do that, so we won't actually use this technique too often, but this idea of level and contour curves is going to be useful to us again in the future, so it's worth spending a little bit of time on right now. So the example is on the next page, page 11. And my goal is to sketch several level curves for the function f of x and y equals 12 over x squared plus y squared, and then comment on the shape of the surface based on what we see with our level curves. So I've given us values of c from 1 to 6. We'll see, we may or may not do all of those. And I'd like to find the equation of the level curve for each of those constants. So keep in mind, when these are values of c, this is to create the plane z equals c that's going to slice through this surface at different heights. So when z is 1, z or f of x and y is 1. And so I would just get x squared plus y squared equals 12. And of course, that's just a circle whose radius is the square root of 12. And just so I can graph it, what is the square root of 12 approximately? About 3.46. So my first level curve, if I come down and graph it, is going to be a circle of radius roughly 3.5. Looking about like that. And I'm going to label that z equals 1. It's a height of 1. All right, let's do this a couple more times. If I've got 2 for the value of c, of course I could again take the x squared plus y squared over. And if I divide the 2 into the 12, this time that's equal to 6. So once again the circle, but this time the radius would be the square root of 6, which is about 2.45. So I have another level curve that's a circle, but a smaller radius. Let's sketch that one. So just under 2.5 this time. A little lopsided in my circles here, sorry about that. All right. We'll do at least 2 more, and then we can maybe start talking about this. If I do a c of 3, so I set the z value equal to 3, I'm going to get x squared plus y squared equals 12 divided by 3, or 4. So the radius of my circle this time is the square root of 4, or not even approximately equal to 2, right? Oops, I forgot to label this last one. This was a z of 2. So a circle of radius 2 corresponded to a z equals 3 up here. And I'm going to do a 4. So this time I'll get x squared plus y squared equals 12 divided by 4, or 3. So my circle has a radius square root 3, or about 1.7 something, right? About 1.73. So my circle is just a little bit smaller, about 1.7-ish here. Something like that, and that was a z equals 4. Okay. And you can see how this would continue. Every single time we do a level curve, we're going to end up getting another circle. Okay. So I'm going to stop right there, and I'm going to talk a little bit about what the original surface must have looked like. I noticed that all of the cross sections are circles, And I'm also going to notice that at the lower elevations, like z equals 1, z equals 2, my level curves are more widely spaced. At the higher elevations, like between z equals 3 and z equals 4, the level curves are more closely spaced. So this tells me that my surface is not going to be as steep at the lower elevations, but it's steeper at the upper elevations. So I'm going to see if I can try and sketch a 3D graph here. All right. By the way, I should probably notice something. Z can't be 0, because if I tried to let z equal 0, I'd multiply the x squared plus y squared over, and I'd have 0 equals 12, which of course doesn't work. So there is actually no trace in the xy plane. Z cannot be 0. So I'm going to start kind of up at the z equals 1, and I'm just sort of show that first circular trace up here at z equals 1. Now my circular contour curves now are going to have to come in. They're getting less and less radius as my elevation increases. And not only that, but they don't go up evenly like a cone. Instead, it actually gets steeper as it goes up. So this thing's going to kind of be dished in. Notice now it's less steep down here, more steep up higher. This is going to actually continue to go up, and my radius keeps getting smaller and smaller, right? This one might have been the, well, this was the z equals 1. This one maybe would have been the z equals 2. And maybe this one was the z equals 3. And if I went up a little bit higher yet, I could have had a z equals 4 as well. All right, what's going to happen if I went all the way in and I've tried to figure out what happens right on the z-axis? Well, right on the z-axis, both x and y would be 0. And again, I'm going to have to go back up here to my function and say, well, wait a minute, that's a problem. If both x and y are 0, I'd have 12 over 0. Not only does that not exist, but if you kind of think about what you know about limits, a non-zero number over 0, that goes to something infinitely large, right, in either the positive or negative direction. And based on my graph, it's pretty clear to me to see that this is certainly going to go up in the positive direction. So this is just going to keep on going up and getting narrower and narrower and narrower. But it'll never actually close at the top. It'll never actually hit that z-axis. So there's always going to be a tiny little hole in the cross-section of the graph. So I think that's probably a pretty decent graph of this function. But let's go ahead and take a look at Maple and see if we can verify that that is really what it looks like. So here we go. I've actually just typed it in so you didn't have to watch me type. I just did my with plots, and then notice there's an implicit plot 3D here. Typed in my function, z equals 12 over x squared plus y squared. And I set my window as -5 to 5 for x and y, and from -5 to 20 for z. Normal axes, and my first try here, the graph looked a little jerky, so I made some extra points. I set my num points, or number of points, equal to 10,000 to smooth it out a bit. A few things. If I tilt this, you can definitely see that hole right in the center there. As we said, it never really hits the z-axis. You can see how it's less steep down low, and it gets steeper up higher, just like we expected. And then also notice, if I can get the perspective right here, this thing just kind of floats above the xy plane. It can't touch the xy plane like we had mentioned. There's one other thing I wanted to show you on this graph. Maybe we'll plot with different styles. This kind of a grid is its default. But if I said style equals surface, it gives me a little bit more of a smooth surface without all of that grid work. I can see that pretty nicely. And there's one other style that you may find interesting because of what we've just been doing. I can also set my style equal to contour. And notice we literally get the contour curves. Going up the z-axis, of course, they're all circles, and if I look straight down at them, now I'm seeing it as though it were a level curve plot, more widely spaced at the bottom and getting super close together here as we get closer to the origin. So maybe we'll do a plot of those contour curves, which if you get the perspective right, lets you see the level curves as well. All right, let's go back to our paper. I'm on page 12 now. And as far as what you'd actually be able to need to do, like for example on a test or something, I won't take the time or have you take the time to actually draw level curves. Instead, what I'm likely to do is to have you do more of a matching problem. I would actually suggest, if you haven't already, take a moment, maybe even pause the video and see if you can match up the surfaces over on the left with their level curves over on the right. And then once you've got your best guess, go ahead and turn the video back on and see if you agree with me. All right, my camera wasn't quite tall enough to get everything perfectly on here, but we can see most of it at least. This first graph, little letter A, if you sliced through with horizontal planes, it would just look like parallel lines, right? Something, and that goes with level curves B here. I'm just going to write the letter. So we've used that one. All right, what about, let's see. Well, actually, I don't know about you. This is one of the more challenging ones for me, but we can talk about it. If you slice through, you're going to get kind of a curve over here and another curve over there. But I don't see any level curves that look like that perfectly. Instead, you also have to think about what happens when you slice down here. Then you're going to get a curve on the y-axis, top and bottom. So actually, I think that's going to be graph E. It's just that what we sometimes want to think of as full level curves, like one piece from each section, is actually not true. The pieces on the x-axis go together. Those are the ones on the top. And then the pieces on the y-axis go together. Those are coming from the ones on the bottom. But it is graph E. So we've used that one. All right. C and E are quite similar, so let's talk about them at the same time. They're very similar shapes. The difference is, in C, notice that the less steep hill goes over the x-axis on the positive side, and in E, that less steep hill goes over the y-axis on the positive side. So that actually tells me what I want to do. For C, I've got to go over the x-axis, so my little ellipses are going to go kind of around that x-axis. And I must actually be talking about graph C right here. On the positive x-axis, notice that they're widely spaced. It's not real steep. But on the negative side of the x-axis, it's quite steep. So on the negative side of the x-axis, these are much closer together. So I think we're looking at graph C here. And then graph A for this one. Again, on the positive side of the y-axis, more widely spaced, not as steep. On the negative side of the y-axis, much more closely spaced, and a much steeper surface. So let's see, that would be A here down for letter E. All right, the last two that we have left are this cone and this paraboloid. The difference in the cross sections, These will become circles when you intersect, and these could be ellipses. So I think D has to go with D. All of the cross sections will be circles. And F has to go with F. The cross sections can be ellipses. All right, again, that's the type of question that you could expect on a homework assignment or on a test from this section. All right, we have one last thing to take a look at. And let me bring this back down so it's not such a mile-high view. There we go. We'd like to take a look at the meaning of a level curve in an application. So suppose this function t of x and y is equal to 40 over 1 plus x squared plus y squared, represents the temperature, so capital T is temperature, at the point x and y. So you can imagine that as you move around this plane at different x, y values, you can plug them in to find out what the temperature is at that specific point. We're going to find and interpret the level curves associated with c equals 4, 10, 20, and 40. And again, I may not actually do all of those. We'll see what we think we need to do. So let's see. We'll start with c equals 4. Instead of z, I have a t this time, but same idea. I'm going to replace it with 4. And if I multiply this over, I'd have 1 plus x squared plus y squared equals, I'm going to divide the 4 over to get 10. So I'd have x squared plus y squared equals 9, or a circle of radius 3. So I'm going to go ahead and color code here. I'm going to do that one in pink. Circle of radius 3. Is my level curve. All right, it also said discuss the meaning, interpret the level curve. So what this is saying is, since I put in a constant of 4 for the temperature, anywhere in the circle, the temperature is a constant value of 4. If I were a little ant walking around this plane, as long as I walk along that circle, the temperature will never change. So temperature is always at 4 degrees. All right, let's do maybe one more. Let's go ahead and let's do the 20. If I put 20 in for the t, again, if I multiply the 1 plus x squared plus y squared over to the left and divide the 20 out on the right, 40 over 20 would be 2. So I'd have x squared plus y squared equals 1. And now I've got a circle of radius 1. So I'm going to go ahead and put this on in blue. Again, this was c equals 4. That's c equals 20. And as far as interpreting, once again, we're saying as long as we stay right on that circle, the temperature stays the same all the time. That temperature is always 20 degrees. So in an application, we often think of those level curves as representing constant values, right? It's a place where the z value, or in this case the t value, doesn't change. All right, down below we have actually a maple graph of the function 40 over 1 plus x squared plus y squared. And the question is, do you think that the three-dimensional graph of the surface or the two-dimensional graph of the level curves is actually a better representation of the situation? And I would argue that in many ways, it's actually the two-dimensional graph that better represents this situation. We aren't actually climbing up a hill. We don't have a true third dimension that we're discussing. We're staying in the plane, but within the plane, the temperature's changing. And I can see out here it's 4 degrees, in here it's 20 degrees. So in a lot of ways, I would argue that the level curves are actually a better representation. The two-dimensional graph is a better representation of what this function actually means. The three-dimensional graph gives a false impression that there's some kind of a third dimension or there's some kind of a hill involved, and there's not. All right, one last thing. This, if you think about it, makes sense as the temperature function if you've got a heat source right at your origin, right? If you've got some kind of a heater right here at the origin, notice it's warmer, C equals 20, a 20-degree temperature when we're close to that heat source, and as we go further out, it gets cooler, and it does so in a very predictable way, right? Right along that circular path where we're the same distance from the heat source all along here, we'd have the same temperature. So this is a fairly logical function, or that temperature function. All right, that is it for section 12.2.